everyone, welcome back to Coding Charms. In this video, we are going to be solving the problem longest increasing subsequence. So we are given with an array numbers and we have to return the length of longest strictly increasing subsequence. So what is a subsequence? Subsequence is nothing but we choose some number of elements from an array which can be continuous or non-continuous. If we take this array, 2, 3, 7 will be a subsequence, or 10, 7, 18 will be a subsequence. Like that, we can pick some elements that can be continuous or non-continuous from an array. That is called as a subsequence. What we have to do is we have to find the longest strictly increasing subsequence. Strictly increasing means all the elements should be in increasing order. They should not be equal also or less than. They should be strictly in increasing order. So let us take a look at the examples. Here we are given with this array. And in this array, what we can do, if we start here, then we can go with 10. We can pick 101. Then it will be, the subsequence will be of length 2. Otherwise, if we start over here, then we can take 2. Then we can take 3, 7, 101. The subsequence length will be 4, or else what we are considering, we are considering the entire array and deleting this portion and this portion and this portion. So that's they have mentioned here. Subsequence is an array that can be derived from another array by deleting some or no elements without changing the order of the remaining elements. Okay. So what will be, or else what we can do, we can consider 2, 5 and we can remove 3 and then we can consider 7, 101. The longest will be of length 4, which can be 2, 3, 7, 101 or 2, 5, 7, 101. And in the second example, we have 0, 1, 0, 3, 2, 3. In this case, if we take 0, then we can also take 1 and then we can take 3. So this will be one subsequence. Otherwise, we can consider 0, 1, then 2 and 3. This will be another sequence, 0, 1, 2 and 3 of length 4. So this is the maximum. So we again return 4. In this, all of the numbers are equal. All of the numbers are 7. Since we have strictly increasing, so we only consider 1, 7. So it will be of length 1. I hope you have understood the problem. Let's see how we can solve it. Let me bring up the whiteboard. Let us consider the example 0, 1, 0, 3, 2, 3. What will be the naive or the brute force way of solving the problem? In the brute force way, we can generate all subsequences for the given array. Then we can check if each subsequence is in increasing order or not. If it is in the increasing order, then we calculate its length and we do that for all the subsequences and keep track of the maximum length of the subsequence increasing. So we finally return the maximum length. So how to generate all the subsequences? To generate all the subsequences at each position, we will have two options: to choose the element or to not choose the element. So firstly, we start out with an empty array. Then we have two options. When first we are at position 0 and the element is also 0. So we choose 0 and we don't choose 0. Similarly, we move to next position. We choose 1 here and we don't choose 1. Again, we choose 1, we don't choose 1. And we move to next position. We have 0. So we choose 0 and we don't choose 0. Similarly, we continue doing the execution and we move to each and every element and choose or not choose. Finally, we will have with all the subsequences. So we check if it is the subsequences are increasing or not. If they are increasing, we calculate the length. Meanwhile, we keep track of the maximum length and finally we return the maximum length to be our answer. So what is the time complexity of this approach? To generate all the subsequences at each position, we have two options: to choose or not choose. So at every position, we have two options. So 2 into 2 into for all the positions. So till n we will have like this. So 2 power n. The time complexity of this approach will be 2 power n, which is exponential, which takes a lot of time. So how can we optimize this approach. So we can use dynamic programming in this case and optimize the time complexity from O of 2 power n to O of n square. Let us see how. So let me write down the example again, 0, 1, 0, T 3, 2, 3. What do we have to do in dynamic programming problems is, first we have to identify the state and the definition and then the formula. So basically what is changing in each step will be the state of the dynamic programming problem. So in this case, at each position we are changing the indexes and we are finding the longest increasing subsequence for that index. We will be doing that. So the state will be the index. Okay, in basically in 1D programming dynamic 1D DP problems, the state will be a single integer, and 2D DP there will be two indexes. So we have two indexes as the state. If we have any other changing variable like cost, etc., then we also include it. So here we don't have anything like that, so only the index will be the state. So dp of I will be the state. What is the definition? dp of I is longest increasing sequence ending at position I. Okay, dp of I means longest increasing subsequence ending at position I. What will be the formula? So if we say, let's say we are at here, this is the ith position, and to calculate the longest increasing subsequence ending at this position, we assume that all the longest increasing subsequence for before elements are already calculated. So we already know the longest increasing subsequences for the indexes 0, 1, 2, and we have to find for 3. Can we utilize the before values to calculate the current value? What is the longest increasing subsequence at first position? 1, and here we have 0, 1. So let me write down 2, and here for 0 we have 1. So we already calculated this. To calculate the 3 value, we use the previously calculated values. So we start from here, we started the first position, and we check 0 is less than 3. So 0 is less than 3. We can extend the subsequence ending at here to include 3. So it will end here now, and the length of that subsequence will be the LIS ending at 0 plus 1. So it will be 2. And next we do it for the next one. So we come here 1. We check if 1 is less than 3 or not. 1 is less than 3. So we consider the LIS ending over here. Previously we have 2 when we check for 0. And now the LIS ending at 1 is 2. And we try to extend it. We try to add 2. So 2 plus 1. The LIS ending at 1 is 2. After adding 3 to it, we get the length 3. So we update the LIS ending at 3 to become 3. Now we move to the next index. We are at here now. So we are at 0th position. What is LI? 0 is less than 3. So we can consider the longest increase in subsequence ending at here and extend it to include 3. So LIS ending at here has length 1. And if we extend it with 3, the length will be 1 plus 1, 2. But we already have 3, so we don't update it. We keep it as it is. So what will be the LIS ending at 3? It will be 3 only. What is that? 0, 1, and 3. So what will be the formula? Formula will be dp of I equal to maximum of dp of j plus 1. We consider all these values as j. Okay, j plus 1, where j is less than I and numbers of j is also less than numbers of I. Then only it will be increasing sequence, right? So this is the state, definition, and formula. Now we can easily code up the solution. So let us code up the solution. Before that, let's see the execution in detail. Okay, so we have 0, 1, 0, 3, 2, 3. Initially, let's consider the LIS here. Okay, indexes 0, 1, 2, 3, 4, 5. This initially we fill the LIS with 1 values because we know we can always consider the 1 length subsequence at each position, and that will always be increasing. So we by default consider the LIS to be 1. At 0th position, we do not have anything to go back, so the LIS will be 1 itself. And in first position, we go back and we have 0. 0 is less than 1. So the LIS ending at 0 is 1. We can extend it by adding 1. So LIS length will be 1 plus 1 now, so which is 2. So we replace this 1 with the maximum value seen so far, which is 2. Okay, let's move ahead, and now we go to the second position. At second position, we have value 0. 1 is greater than 0, so we don't consider it. And here 0 is equal to 0, so we don't consider it because we want strictly increasing. And next, we move this arrow to the front. Next position, which is 3. So 3, we come here and we check, right? 0 is less than 3. So what is the LIS ending at 0? 1. 1. If we extend 3, we will get the length 2. So we replace it with 2. The maximum is 2. So we update the LIS at third position with 2. And then we come to 1. LIS ending at 1 is 2. So 2 plus 1 will be 3. Now we got another maximum value. So we update the LIS ending at 3 to 3. And we move on to 0. When we move to 0, what is the LI? 0 is less than 3, so we can consider this number. And what is the LIS ending at 0? 1. Its length is 1, so 1 plus 1 is 2, but we already have 3, so we don't update it. So finally, the LIS at position 3 is 3. Now let me remove this as well. Okay, now we move to the next position, to 2. Fourth position, which has value 2. We can iterate over all of these now. 0 is less than 2, so we can compute 1 plus 1 will be 2. So we update the LIS with 2, and then we move to here, first position. At first position, we have LIS 2. So if we extend, 1 is less than 2, so we extend it. 2 plus 1 is 3. We again update it to 3. And now, okay, now we move to next position, 0. And at 0, LIS ending at is 1. 1 plus 1 will be 2. 2, and we already have 3, so we do not update it. Now we move to the next position, which is 3. 3 is greater than 2, so we don't consider it. So finally, the LIS ending at 2 is 2, 3. Sorry, 3. What is the LIS? 0, 1, and 2. Okay. Now, let me remove all of this. And now we move to the last position, which is index 5 with value 3. So 3, we iterate over all of this again. 0 is less than 3. So we can consider this 1 plus 1, 2. So we update the LIS with 2. And again, we come to first position. At first position, we have LIS ending 1 is less than 3. So we can consider it, we can extend it to include 3. So 1, 2 plus 1 is 3. So we update this 2 with 3. And now we come to 0. 0 is again less than 3. So we can extend the LIS ending at the second position. So 1 plus 1 is 2. But we already have 3. So we don't update it. Here we are 3 equal to 3. So we don't consider this. Again here 2 less than 3. So we can consider this. What is the length of the LIS ending at 2? It is 3. We add 3 to this LIS. So we extend it by 1 length, so we add 1, and the length will become 4, and we update 3 with 4. Finally, the LIS ending at 3 is 4. So the LIS can end, the maximum value can get in any position, right? So we take maximum of LIS of I. So we keep calculating the maximum LIS, and finally we return this maximum LIS. So we can get the maximum length LIS in any position. It's not guaranteed to be at ending position only. Suppose in the example we can have 1, 2, 3 and 0, 0. At this case, suppose this is the array, then LIS will end at this position. So we have to keep track of maximum LIS of all the indexes. So we keep track of maximum LIS and finally we return it. What will be the time complexity? So we are going through array only once, and for each time we are calculating all the before values. So we have two nested loops. We will have two nested loops, so the time complexity will be O of n square. What will be the space complexity? We are having the LIS array, so the space complexity will be O of n. So let's code it up. Let's start by calculating the length of the numbers. So n. Next we have to have a DP array, DP of n. Initially all the indexes have LIS of length 1, so I have initialized it with 1, and then for int I equal to 0, I less than n, I plus plus, and now we again iterate over the before numbers. So j equal to 0, j less than I, and j plus plus. If we check now, if numbers of j is less than numbers of I, then what we do? dp of I will be equal to maximum of dp of I comma dp of j plus 1. We try to extend the LIS ending at j with the current number. We also should have a maximum length variable to keep track of longest increasing subsequence. So initially, let's say it's 0, maximum length equal to maximum of maximum length comma dp of I, and finally we return the maximum length. Let us run the code. It passed all the test cases. Let us submit it. It passes all the test cases. As discussed before, the time complexity of this approach is O of n square. Since we are having two nested loops, and space complexity of this approach is O of n because we are having a DP array. I hope you have understood this problem. This is the standard problem, and based on this problem, many problems are built. So if you understand the standard problems, you can solve other problems easily. And if you did understand today's video, make sure you hit that like button, and more daily videos, subscribe to Coding Charms and keep practicing. See you all in my next video. Till then, take care. Bye bye.